Mike and Ron here, shooting live from the Middle East. We're in Israel in the Dead Sea. Jordan's over there. To give you a brief geographical, historical context, all of these mountains that surround the Dead Sea have lots of salt and minerals in them. After thousands of years of runoff water coming into the sea, all of that salt and minerals got collected, and now it's 34% salt. That's 10 times more than the sea. And that leads to a lot of cool physical properties.
In particular, what these properties are called are colligative properties. Properties of a solution that depend upon its concentration. Common ones are boiling point and vapor pressure. But what's cool about the Dead Sea is its density. You can float here like nowhere else.
Nowhere else.
Check it out.
When we start thinking about solutions, it's best to start bringing up the analogy of a ball on a hill. A ball will want to minimize its potential energy, PE, by minimizing its height, h, and falling down the hill. Similarly, solutions will want to minimize their potential energy, and the potential energy of solutions is called the Gibbs free energy. The Gibbs free energy, G, is given by your enthalpy H minus your temperature T times your entropy S. Now, you may not have heard of what entropy and enthalpy were before, but we'll give you some simple explanations so you can remember them. Your enthalpy is given by how much heat you need to put in to form something. So if you think about it, you need to heat up a solid to form a liquid. You need to heat up a liquid to form a gas. So the enthalpy of the solid is the lowest, the enthalpy of the liquid is in the middle, and the enthalpy of the gas is the highest. The entropy is the measure of a disorder in the system. If you think about it, gases are really disordered. They're all over the place, so they have high entropies. Liquids are in the middle, they're kind of ordered, kind of disordered, and solids are pretty ordered, so they have the lowest entropies. If you notice, the only thing you can change in the equation for the Gibbs free energy is the temperature T.
So now, let's think about how the Gibbs free energy changes with temperature. First, there's a solid, whose energy doesn't change much with temperature. Then, the liquid phase, whose energy changes much faster with temperature. Because it's more random, there's more entropy. Where the two lines intersect is the freezing point. Beyond this point, the solid can lower its energy by transitioning to the liquid phase, and that's why we see liquids above this temperature. Next is the gas phase, with even more entropy. Now again, the intersection of the two lines is the boiling point, because the liquid can lower its energy by transitioning to the gas phase above this temperature. What happens when we add salt to a liquid is that we lower the enthalpy of the liquid phase, making a new energy versus temperature line, L prime. A consequence of lowering the enthalpy is that the freezing point has decreased and the boiling point has increased. Since all of the lines are linear, and the change in the enthalpy is linearly proportional to the change in salt content, the changes in freezing point and boiling point will be linearly proportional to the changes in salt content.
Let's enter the lab and show how the freezing point of water changes depending on how much salt we add to it. We're going to make 3 solutions with different salt concentrations and then measure the freezing points. Our first solution is deionized water, which is purified not to have solutes in it, and it should have the normal freezing point of water. The next solution is a 0.1 mole salt solution, which will show us what adding a little bit of salt will do. We need to dissolve it in water so that all of the salt is dissolved in solution. Last, we have a 1 mole solution of salt, which is 10 times as much salt as before. Look how much salt that is. We then put all 3 solutions in the freezer and waited for them to freeze.
Now that all of them are frozen, we sought to measure the melting points of all 3, starting with the no salt, which measured 0 degrees Celsius. Then we moved to the 1 molar, the most salt, and we noticed a very big drop in the melting point. If you look, that's almost -6 degrees Celsius. Then when we moved to the 0.1 molar, we observed that the freezing point was only slightly below 0. Using our measurements, we constructed a graph of the freezing point depression versus concentration. As you can see, our trend was the same as with theory, but we measured too much of a decrease.
Bringing it back to why you can float so well in the Dead Sea, we also performed a brief experiment to determine the density of the solutions. It was really simple. We just weighed 10 milliliters of solution in a graduated cylinder and then calculated the density, which is the mass divided by the volume.
As you can see, there was significant error in our density measurements, but we still show an increasing trend of density with concentration, just like in the Dead Sea.
Thanks for watching.